Okay, in our previous video, we were talking about um, having a normal distribution we were working with the underlying normal distribution where we had a sample size that was greater than 1. All right, but the underlying distribution had to be normal. Well, here we're going to talk about central limit theorem. The central limit theorem is probably the most powerful part of all statistics. And the reason it is it indicates, because we know that not everything is normal. Some things are uniform, some things are binomial, some things are geometric. In fact, earlier this week, you were working with geometric and binomial. All right, so we know that not all distributions are normal. However, with central limit theorem, things become normal. All right, and you're like, wait a second, how does a highly skewed or a binomial become normal? Well, first off, let's talk about what central limit theorem says. It states that the sampling distribution of the expected values of a population with a mean and standard deviation will be normal for any population, in other words, regardless of the shape, if the sample is large enough. So if we have a large enough sample, the distribution of the means. When I say distribution of means, I'm talking about the distribution of the averages or the X bars. So the distribution of the X bars will become normal if the sample is large enough. They're like, well, how large is large enough? And we say 30 or larger. If it equals 30, it's large enough. 31 is great. 29, not big enough. Okay? So the distribution of sample means is normal. We say the population mean equals the sample mean, and the standard deviation is still this. And we're still going to be working with the previous formula. So that should make you feel a little better. All right? So why is it important? First off, the reason it's important is we know all the probabilities associated with a normal. Matter of fact, that's what we've been doing, is calculating those probabilities. And so because if we can say that everything becomes normal when we work with a sample size 30 or more, that means we can use everything that we know about the normal, and we can use all the stuff that we've learned prior about the normal. Okay? So I'm going to want you to read this entire page and ask questions about it as you need to. But there are a couple things I want to point out to. Conditions necessary to use the normal for the distribution of sample means. 1, you must have a simple random sample. The population must be normal, or the sample size must be at least 30. Okay? And we need to be talking about X bar, or the averages. Okay, really important that we're talking about X bar and the averages. We need to know the standard deviation of the population, all right? And they need to give us the mean. So let's try this out. Now, because there's a lot of writing on this and I don't want you to have to wait on me to write everything, I'm going to use some pre-printed answers. All right, so I'm going to slide those up as we go along. So the distribution of household incomes in the United States is skewed to the right. So that right now, they're telling me it's skewed to the right. I may remember, you should remember, that skewed to the right means it looks like someone stretched it way off to the right. All right? So this isn't normal. It's not a normal shape. It's been stretched to the right. The mean of the population is 71,500, and the standard deviation is 26,200. Determine whether or not central limit theorem is appropriate and identify the mean, the standard deviation, and the shape. So listen very carefully because this is tricky, especially on this first one. All right, especially the first one. So a sample of 100 is taken, and I'm sitting there go bing, bing, bing. This is great, This is n equals 100. That's greater than 30. Sounds like central limit theorem probably is going to work. And it says, what is the shape of the distribution of sample values along with the mean and standard deviation of the distribution of the sample values? That's a key distinction. They did not ask for X bar. They did not ask for the average. They did not ask for the sample mean. All right, this is why this is tricky. Central limit theorem does not apply, even though we have a sample of greater than 30, because we're talking about the distribution of the sample values as opposed to the distribution of the sample means or X bar. So in this case, they were trying to fool us. Now that doesn't happen very often, but because they said sample values, it follows the underlying distribution. So my mean is 71,500 and my standard deviation is 26,200. And because they're talking about the shape is going to be the same as the underlying distribution because sample values always follow that of the population. Sample means become normal. So write this down. Sample means are normal for n greater than or equal to 30, for n at least 30. But they didn't ask for sample means, they asked for sample values. That was tricky, okay? We're usually not that tricky. So the next one, a sample of 25 is taken. What is the shape of the distribution of the sample means? Bing, 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 winner, winner, chicken dinner. We said sample means, that's X bar. Okay. Central limit theorem applies if n is greater than 30. Oh, it's 25. It's too small. So central limit theorem doesn't apply. We are talking about sample means, and that's good, but our sample size isn't big enough. So in this case, central limit theorem does not apply because the underlying is skewed and our sample is less than 30. Our mean is 71,500, and this is actually a typo. This should say 26,200 divided by the square root of 25. That's what that should say. The distribution of is not normal because the sample is less than 30. A sample of size 110 is taken. Hey, that sounds pretty good, 110. What is the shape of the distribution of these sample means? Hey, they asked about X bars. In this case, this is greater than 30. They asked about the sample means or X bars. So central limit theorem does apply. Central limit theorem does apply. And this is 71,500. This is 26,200 divided by the square root of 110. All right. All I did was take the given standard deviation of the population and divide it by the sample size of 110. And our shape is normal by central limit theorem because n is greater than 30. All right. Finally, a sample of 50 is taken. What is the shape of the distribution of the X bars along with the mean and standard deviation of the X bars? Hey, this is n equals 50. That's greater than 30. And they asked about the X bars. That's the sample means. All right. So they asked about the sample means. So guess what? Central limit theorem applies because n is greater than 30. Our mean is 71,500. Our standard deviation is 26,200 divided by the square root of 50. So this. And our shape is normal. And the distribution of sample means is normal because n is at least 30. All right, so real quickly, here's the thing. If the underlying distribution is normal, we're good to go regardless of the sample size. If it's not normal, so in this case it wasn't normal, we have to be talking about the distribution of the sample means or averages or X bars, and N has to be greater than or equal to 30. So if the underlying distribution is normal, you're golden, just go ahead, that's fine. If it's not normal, we have to be talking about the sample means, and N has got to be greater than 30. If so, it all becomes normal and we get to by central limit theorem. The central limit theorem is probably the most powerful thing in statistics, so it's really, really important that you understand that.